Our fourth big topic in this lesson is on local linearization and tangent line approximations. This is something that you're all used to, so this model problem should be pretty straightforward. If I have a function, sorry, that's my dog. If I have a function defined as e to the 3x, and I'm asked to use the line tangent to the function at x equals 0 to approximate f of 1, then what I'm going to need is two things: a point of tangency and a slope. The only way I'm going to be able to build the line tangent to the graph is with these two characteristics. So because the line tangent is being built at x equals 0, my point of tangency has an x coordinate of 0. Sorry, that's an ugly 0. Oof, let me try again. Has an x coordinate of 0, and it's my job to find the y. And then in a minute, when I want to find my slope, it's going to be necessary to compute the derivative. So back in Algebra 1, when we were required to find points on a graph, if I had an x and I needed a y, the simple process for identifying the y value was to plug the x into the function. So for us, that leads to e to the 3 times 0, or e to the 0, which is 1, which allows me to complete my point of tangency over here as 0, 1. No big deal. If I can make the connection that the slope is just the derivative, then the work that's going to be required here is to find f prime of x. This is a nice chain rule for the exponential function, so f prime of x is e to the 3x times 3, and I need the slope at our point of tangency, so I'll plug in a 0. That's e to the 3 times 0 times 3, or e to the 0 times 3, or 1 times 3, which is 3, which allows me to come way up here and classify my slope as 3. So the tangent line to the function at x equals 0 is simply y equals 3 times x minus 0 plus 1. And if I'd like to approximate the function value at 1, I'll use my tangent line to get my approximation. And that's that. And moving on now to key lever number 5, the mean value theorem. You'll see in your notes here that mean value theorem is laid out for you. It states that if a function is continuous and differentiable, then there exists a value in between a and b such that the derivative at c is equal to the slope between a and b. That's just a rise over run computation over there on the right. Visually, what that's telling us is that the slope between any 2 points on a continuous and differentiable function, that slope right here, is guaranteed to be equal to the derivative, which is the slope of the tangent line, somewhere in the interval. So you can see that those two lines are parallel because their slopes are the same. As long as the function's continuous and differentiable, that's a guaranteed known fact about the function. The slope between the endpoints is equal to the derivative somewhere in the middle. So in this first model problem, if we have a continuous function called g that's also differentiable on the intervals -1 to 3, and if we know that we have two known values, -1 is equal to -10, and at 3 we're equal to 6, we want to try and determine which of the following statements must be true. So those key words, continuous and differentiable, kind of like set off a radar in my head that make me think of the mean value theorem, because those are such important words in our theorem up above. So what I know is that at one endpoint, the value that we have on our graph is at -1, -10, and the other endpoint is at 3, 6. So according to the statement on the mean value theorem up above, this first statement that I want to consider is, will the derivative ever equal 0 somewhere on this interval? The only way to show that the derivative has to be 0 would be to prove that the slope between these 2 points is also equal to 0. So let me do a slope computation real quick and see what we come up with. My change in y over my change in x. And up top I think I get 16, and down low I get 4. When I divide that out, I see that the slope between my endpoints is actually equal to 4. So what the MVT states is that this slope of 4 right here is going to have to equal the derivative at some point where c is in between -1 and 3. Those are the two x values that were given with these 2 points. So this is a conclusion of the mean value theorem right here. And that actually looks a lot like number 2. G prime of c is equal to 4 for some value inside of our interval. And you can see I misspelled the function right there. Sorry, that's supposed to be a g. What I can't guarantee is that first statement. There is absolutely nothing saying for sure that the derivative will equal 0 somewhere in the interval. So that's untrue. That does not line up with the slope computation that I just showed you. The third statement here actually has nothing to do with the mean value theorem, because if you'll notice, there's no prime on that g right there. So this is just saying perhaps a picture would help us out. If on one side of the graph I have a point at -1, -10, so that's somewhere like way down here. And on the other side of the graph I have a point at 3, 6, that's somewhere up top. Sorry, that's really hard to see. There's one point, and the other one is way down here at -1, -10. Why is it doing that? Down there and up here. This just says, with those two endpoints, will there be a value on this function equal to 4? Well, remember, this is up here at 6. This is down here at -10. So if this continuous function is defined for all of those values, is there a place where the function has to be equal to 4? And I would say, well, of course, it's right here. That's actually according to the IVT, not the MVT. The IVT is the one that states that if my function's continuous, I'm guaranteed to exist at all those y values in between -10 and +6. All right, and so the second model problem still aligns with the MVT. Let the function f be defined as x cubed plus 5x. For what value in between 1 and 3 does the instantaneous rate of change equal the average rate of change? So a quick note, instantaneous rate of change is synonymous with derivative, and average rate of change is synonymous with slope. So what this question is asking is, when will my derivative equal to my slope? So in other words, at what value will my function's derivative be equal to my function's change in y over change in x? So this is a really nice MVT question. Well, my derivative for this function is 3x squared plus 5. So I'd love to know when that derivative is equal to f of 3 minus f of 1 all over 3 minus 1. In other words, 3x squared plus 5 needs to equal to, let me do some side work. F of 3 is 3 cubed plus 5 times 3, or 27 plus 15, or 42. And f of 1 is 1 cubed plus 5 times 1, which is 6. So what I'm trying to figure out right now is when 3x squared plus 5 will equal 42 minus 6 over 2. So when will 3x squared plus 5 equal 42 minus 6? I think that's 36. 36 over 2 is 18. So let me keep solving here. That means 3x squared needs to equal to 13 if I move the 5 to the other side. x squared needs to equal 13/3, and x would have to be plus or minus the square root of 13/3. Since my answer has to be on the original interval 1 to 3, then I'm going to make my final conclusion that the x value that satisfies the mean value theorem is the positive square root of 13/3. Not the negative, because that won't fall in my window. All right, last key lever here is the extreme value theorem. If f is a continuous function on the closed interval a to b, then that function must have an absolute max and an absolute min on the interval. And here's how we can find those absolute minimum and maximum values. If y is equal to 2x minus 8, determine the smallest value of the function p equals x times y. Another way of writing p would be p equals x times 2x minus 8. Well, that's an 8. The reason I'm able to make that connection is because the y right here I'm replacing with the way that y is defined. So let me clean that up. That's 2x squared minus 8x. To find the absolute minimum and maximum, the first thing that we're going to want to do is find the derivative of our function. The derivative here is 4x minus 8. We're going to set that derivative equal to 0 and solve. What I'm seeing in this problem is that a critical value occurs at x equals 2. That means x equals 2 is either a minimum or a maximum. And in order to continue on with the process, I'll do a quick number line test, put a 2 on it, choose a test value to the left of 2, I don't know, maybe like 1, and a test value to the right of 2, like 3. If I plug this test value in right over here into my derivative, I'm going to get 4 times 1 minus 8, which I believe is 4 minus 8, or negative 4. And I see that on the left of 2, I get a negative derivative. If I do the same thing at 3, plug in my 3, that's 4 times 3, or 12, minus 8, which is positive 4. And this is confirming that on the other side of 2, I have positive derivative values. So since this p prime number line changes from negative to positive, what I'm able to capture is that x equals 2 is the location of a minimum. X equals 2 is a min because p prime changes from negative to positive. That's where the minimum occurs. This problem actually asks me to find the minimum value. So to figure that out, I'll go plug 2 into my original function. That's 2 times 2 squared minus 8 times 2, or 8 minus 16, or negative 8. What that means is that the lowest value on this function is happening at a y-coordinate of negative 8. This problem doesn't specify an interval, so I'm just being very conceptual and vague here and checking my critical value, and that's it. But had there been an interval given, I would have also had to come over here and check my endpoints so that I could see if that negative 8 truly is the lowest value. So we'll talk about that more in class. We have to always check our endpoints on these examples too. All right, that's all of my key levers. I know this was a lot on these videos, so I appreciate you hanging in there. Go ahead and attempt the multiple choice questions and you'll get some feedback first thing tomorrow.